So, welcome to the third keynote lecture. Please take seat that we are going to start. Okay, so I am very honored to introduce the third keynote speaker, who is Professor Giovanni Bosco. He is a professor at the University of L'Aquila, and he is professor of geotechnics, and in particular he teaches slopes stability. He is a pioneer in Italy in facing very challenging geotechnical problems in more than 20 wind farms onshore that have been designed and constructed in the south of Italy and the center of Italy, like in Apulia and Toscana and Calabria, I think, and so on. Okay. So I will give the floor to Giovanni and enjoy.
Thank you very much. Thank you for this very nice work. Thank you to the organizing, very impeccable organizing. Thank you to you for being here. I will not call your attention if you fall asleep. It is after lunch, so it is, I would say, difficult to fall asleep a little bit. I will focus on the geological and geotechnical aspects of 4 wind farms in this area of Calabria. And I have broken the presentation into 5. I have one general presentation, which is the one I will be showing right now, and then I have a presentation for the different 4 wind farms. I will begin with the wind farms we are going to visit tomorrow morning as first. If there is time, I will go on with the other wind farms. And you are welcome to have copies of the presentation. You just send me an email. I have my email address over there. Okay? The work I've been doing with Professor Borri, Paolo Biagini, and Dr. Bruna has been that of defining the subsoil condition of the different towers, different turbines location for these 4 wind farms, besides other I will not talk about today, and getting soil properties in terms of characteristic values to design foundations. We have been designing 2 types of foundation, a shallow foundation and a deep foundation. In these towers and in this geological setting, the main issues are over there. Wind and earthquake loadings, sites usually faulted and crossed by tectonically active faults, variable soil and rock condition, layered soil and rocks, and instability problems. When I say soil and rock, I mean material that can be broken into single particles with your hands and by wetting and drying it, or material which will not break but may be broken into fragments by tectonic actions. This poses difficulties in terms of the variety of failure mechanism and difficulties in terms of subsoil investigations. Very helpful in this case is geological investigation, especially when we have instability problems, because it is easy to concentrate the subsurface investigation at one tower location. It is difficult to expand the subsurface investigation away from the tower for 2 reasons, operative, operational, and cost. Typically the investing person, the people who is paying for the wind farm is willing to minimize cost, obviously, and so he is concentrated to the location of the single tower. He doesn't care very much about transportation facilities and away from the tower. And people tend to overlook the instability of large soil mass that would include deep foundations. The geological help is in recognizing, and this is, I think, it's the major objective, to recognize instability on a larger scale. Subsurface investigation is usually carried out in this area through drilling, and calculations are based on data retrieved from laboratory tests on soil samples, disturbed or relatively intact samples due to the typical layering. In situ investigation is usually not possible. We do have now a variety, I would say, overwhelming amount of laboratory investigations, and I have here a collection of some. We do have, at the same time, a great variety of in situ field testing procedures. The point of is this. In case of laboratory testing, the difficulties of retrieving undisturbed samples or samples that even they are disturbed, they retain those properties, those in situ properties that we are looking for. In the case of in situ testing, the problem is to pass and penetrate stiff layers where you cannot advance a cone, a dilatometer, and where you, if you want to advance them, you will be obliged to drill and then advance. Okay? In the case of geophysical investigation, the limitations are the interpretation of surface wave measurements due to layering, especially when layering is not horizontal as we are used to, but it is inclined due to tectonic stresses, or there are parts of the subsoil are displaced, dislodged due to past tectonic movements. We have used typically downhole test to get a measure of the stiffness of the material. We are talking obviously of stiffness at very low strain, the strain connected to a wave propagating. This should be supplemented with laboratory tests to determine degradation moduli and so on, which are obviously difficult to execute. Now, after we have these premises, I would like to tour the different wind farms. In my opinion, I had imagined that we were touring from south to north, but since our first stop tomorrow is on the northern part, on the most northern wind farm, I will probably switch it. The reason why I was touring from the south to the north is that soil conditions are somewhat similar in the sense that there is probably a worsening of the soil condition moving from the south to the north. So I will concentrate on Ciro, CIRO, where we have 13 turbines. In origin, the wind farm was a 16 turbines wind farm, which was reduced to 13 due to environmental and difficulties. And afterwards, if there is time, I will start moving south. Okay? So that is it. Now I will try, if I can. Glasses first. Grazie, thank you for your help. We will now show Ciro. This is the area of Ciro. I will pull out the geological part afterwards. These are Google Maps, obviously, picture from Google Maps, but if you look at them, this is a picture of 3D, but if you look at them, you see a very, very rough terrain. You will see it in comparison with other wind farms. Variable soil condition, you can see landslides over here, movements over here. This is the major road coming to the wind farm. Okay, the park is towards the left over here. Now I'm moving from Ciro along this road towards the park. In this hairpin bend, there is slides over here affecting the road. What you see here are locations of the initial design, initial project of this park. They have been changed, they have been switched a little bit. If you look at this one, which is one of the first, you see there is a steep area over here. What you see here is essentially large landslides, and all large landslides which now this element apparently is stable and it is used for agricultural purposes. Okay? The park ends more or less here, where we have a shallow foundation tower, number 10. This is tower number 1. What you see is that the area of the tower is very close to a sloping area, which relatively steep at some places. Obviously, the inclination of the ground depends on the soil condition, and we do have over here a mixture of soil condition. This is material that has been excavated, but if I look close to this material, this is now a view of the area. You see, it doesn't seem very weak. It can stand vertically. So these are layers of sandstone, which is some other times called calcareite, which is a cemented sand, sometimes with very tiny pebbles. It was an undersea level deposit, and it was cemented by calcareous deposition from old fossils. Sandstone with slightly cemented sand on top and sand on top. Okay. The reason why the foundation here is on piles, despite the strength of the material, is the vicinity of the slope. And the reason why we selected in some cases the pile foundation instead of the shallow foundation is to keep it smaller. The pile foundation is 16 meters in diameter. The shallow foundation is 18.5, and excavating on these steep areas when you have a large foundation is costly. This is tower number 2. Behind here there is the sloping ground as in number 1. We see the similar formation as before over here, and from from these big gabion walls, so you can get a feeling of the excavation that was required to reach foundation level. You see the steep slopes over here. This top here is stiff sandstone and stiff marly clays, which is standing vertically. At the base, this is the debris coming from weathering and degradation of the material. You see that the terrain is relatively rough, and what is fun is that roads have been laid on top of the hills, because this is the least affected area from instability. Instability starts here and then goes backward. Tower number 3, similar soil condition with exposed stiff clay and marly materials. This is tower number 4. As before, you can see an upper layer of yellow sand and sandstone, and the marly clay with thin layers of sandstone. Performing field testing in this material is essentially impossible, because when you hit this rock-like material, you will not advance. Drilling is the only possibility. Getting intact samples is impossible, because the thin tube will just buckle or bend, so you will not retrieve anything. So you cannot retrieve what is called undisturbed samples. What you can maintain probably is grain size composition, which is not very usable. The point is that probably we don't even keep undisturbed water content, which is very low in this material, and it is responsible for this high strength of the clay material. Designing piles in this condition is, I would say, not very easy, because we don't know the pore pressure. Very likely pore water pressure are negative in this environment. We have not encountered water. Very likely water is down below towards the valley areas. So these materials are either unsaturated or unsaturated with very low pore water pressure. And so estimating the strength is only possible through unconfined compressing test of triaxial U test. And we used the undrained shear strength to determine the lateral shear strength along the pipes. The other peculiarity is the different kind of materials that we encountered in these areas. Okay, very close to slopes, close to area where there is a relatively peak. This is typically of the stronger soils. Okay, and again layering of sandstone within the clay mantle. We have been able, one thing that is fantastic of looking at this large excavation is that you understand how narrow, how limited is the information we get from boreholes. Even if we have a large amount of boreholes, it is very unlikely that you could see a fault as we see over here. You see that this material has been dislodged with respect with the nearby material. So we were very lucky to look at the excavations, and the reason I'm showing this picture is because we will not see them tomorrow, because the tower, the excavation area of the tower has been filled. So this is an opportunity to have a large view of the soil and to think about, when we talk about boreholes, how limited is the information. Tower 6, similar condition, but very, this is the superficial stiff soils, when it gets in contact with water, when it is wetted by rain, it degrades very quickly and loses most of its strength. In the vicinity also of the slope is a reason why this tower is on piles. Another of these towers where you see the layering, and from the stains I can see here there must have been in the past water circulation along this fissure. Now a question might be, are these fissures, do these fissures follow a orientation? Are they from a structural point, as we say in rock masses, iso-oriented? Is there preferred orientation? We did not investigate these aspects, and most of them are generally vertical. Those which are horizontal are not steeply inclined. This is difficult to survey with the classical compass that is used to survey discontinuities. This is Tower 8, very close to Tower 7, and you see after excavation and after exposing the material to rain, how the aspects, how it changed, and how quick is the degradation of its strength. Okay. 13 towers. We will go rather quick so that I can show some of the things. So we will see this, we will not see the soil, we will see the areas. So we will see this kind of terrain. Towers 12, 13 are close to the road, on top of the hill. As you see, the road is down here, and the area of the tower is this one here. Okay? This is a view from Tower 12. No, this is not 10. This is 12. That was a mismatch. Deep excavation. Vicinity of the slope. Also for tower 13. Then we move to tower 14, and here we encountered water close to the surface. And you can see the wetted layer below a superficial layer. The information we have in terms of water circulation are nil, because the variety of the soils does not make it simpler, and because we don't have a network of piezometers and not only standpipes, but essentially 4 water pressure measurement piezometers to understand what is going on. So the simplification led us to consider a water table over here, assuming the water table 2 meters above the level of the foundation, thus reducing the strength of the material and running a effective stress analysis. Okay, in the remaining 5 minutes, I might see if I can get out from the presentation the information. Devo vedere se ho le informazioni sulla geologia. Mi faccio vedere che cosa abbiamo caricato. Sì. Sì, non so dove è andata, mi mancano le parti. Vabbè, vediamo. Dove ci fermiamo? Professor Porri, what is the second stop tomorrow after Giro?
Scandale, Fortino Santa Domenica.
Okay, we'll make a quick review of 14.
I hope the meteorological condition will allow it.
This is a windy area, so otherwise we would
We
not
are
have
not
a wind
seeing
farm. Okay?
in a new landslide.
This is, there are 2 wind farms very close to each other. This is called Il Fortino. Close to this one there is another area. In another wind farm. In the second wind farm, which is called Santa Domenica, all towers have shallow foundations. This may be an interesting point because we came in the design project after the investigation had been conducted, and so the group designing the foundation did not decide the investigation program. And the client asked us to work with the investigation that we were provided by the client. And I think it is useful to understand that we can do investigation afterwards, but in some cases this would end up with a cost increase, besides the time consuming. The material is similar to what you have been looking at, because now we are moving south, and what is typical of this park is this very stiff clay soil, which is covered by different sandstone, sand layers at some depth. Now I'm saying at some depth, but some depth may be superficial, because this region has been cut by faults and it has been subjected to tectonics. So something that was 1,000 meters below the sea is now emerging, it's now outcropping, okay, in some place. In another place it is still resting 1,000 meters below because it was not pushed up, okay, more or less. I apologize for the bad geology, okay. So you see very similarity in these very stiff marly soils. And you see the excavation that soon after the excavation can stand up almost vertical, but must be protected afterwards because the material degrades with precipitation. And what you see here is this tower, a very thick layer of sand extended about 16 meters below this level, and then there are the stiff clays. Okay, pile testing was executed just to figure out if limited soil information had allowed an acceptable design of the piles. These are cross holes to check the integrity of the piles, and there were never problems in terms of integrity of the piles, even if piles were bored on where solid recasting place, where by pouring concrete with a tiny pipe inside the hole. Some of the things I'm not saying, you can read it in the paper. This is the first load test. In what we see that the load carried was 4 meganewtons at a comparatively little settlement. I don't know why we don't have a rebound curve. This is a mystery. So by estimating the failure load, we came out with a very high load, which is much greater than the design load. Okay. And the second site, where we didn't have the sun emerging on top, what we see is that with a relatively small load of less than 4 meganewton, we already got almost 15% of the diameter in settlement. So this foundation was not considered adequate for the tower. We extrapolated using the hyperbolic reconstruction a possible limit failure, and we came up with a failure load between 4 and 5 meganewton. If you apply the factor of safety, then you obtain much less than the design load. So what we did is that we switched the type of foundation. Instead of considering it a foundation on piles, where the piles would be carrying entirely the load from the tower, we switched it into a shallow foundation, which is allowed by the code, where the piles are used as settlement reducer. Okay, so this costed in terms of times, and in terms of redesign, in terms of preparing a new design and sending to the so-called genio civile and whatever. Okay, I think we can stop here so that I don't take too much time, and for any other information regarding the other wind farms, feel free to give me a call or send me an email, and I will send you a copy of the presentation. Okay.
Thank you.
Thank you.
Thank you. Thank you. So I think we have time for some questions or comments or curiosities.
I may have a comment, a general comment that possibly concerns not only our country and the people that are working in this country, but mostly the community of engineers that are dealing with development and design of wind farms, or onshore and offshore. The time has longly passed where engineers dealing with this were mainly industrial, mechanical engineers. As you have seen, and the purpose of this presentation was to convince that if you take a wind farm with 100 million euro of overall budget, of these 100 million, almost 70 or 80 are civil engineering works. Because the civil engineering relevance of these large structures, large means over 100 meters of a tower, rotor blades that now pass the 100 meters of diameter, the structures for transporting electricity, the structure of consolidating solar foundations, under foundations, piling, etc. And if you think in terms of offshore, then even more. So the civil engineering component becomes dominant in terms of works and competencies. And that is somehow something that I have experienced on my scheme. Coming to a group when they ask me for advice for putting the design, etc., I have always to talk with people that have nothing to do with civil engineering. And they tend to neglect the problems, not only the authorization problem, but also the problems on the construction sites. So Giovanni Bosco is one of the most heroes, because two of us, but mainly he, is the main advisor for the foundations of all these wind farms. We had to convince people about solutions, about etc., facing the problem of having big amount of money in the game. And people tend to say, oh, what is civil engineering will be peanuts. So that is these are the boundary conditions where professional engineers are operating in this field. Okay, sorry, that was a comment. And let's say my idea to have Giovanni with us in order to make evident what is sometimes is not evident at all.
I agree with you. My view is that engineering, designing, is a process like going to surgery. We will need the most efficient and capable figures in the surgery room. It's not only the person who is mechanically, I would say, doing the surgery. We need the history of the illness, we need person capable to understand analysis. It is the same. It's a process in which the different figures involved must work together and find a solution which will cover the different aspects. I've heard this morning that we shall not overlook the possibility of earthquakes and winds acting together.
Yes.
Okay. I've heard that with the reduced cost of electronic equipment, we will be soon overwhelmed by an amount of a mass of data where we will be lost. So we need the system to analyze data, to analyze a large number of data, to understand if there is a fault in the instrumentation, or if there is a fault in interpreting data. So this makes the group of people involved larger, and which is understandable. We are making things more complex. It didn't take very much to drive a car with a horse. Now it takes much more to drive a shuttle bus towards the moon. This is clear. These structures are becoming more and more sophisticated because we are constructing them under more and more difficult conditions. So we must have knowledge and we must have an enlarging group of people working together. Okay? Thank you.
Thank you.
Thank you.